In this video, we're going to learn how to represent shifts in an equilibrium system on concentration time graphs. The equation that we're going to use as a prototype is the synthesis reaction of NH3 from nitrogen and hydrogen gas. And the stimulus we're going to apply to this reaction is a concentration increase in NH3. This means because we have more ammonia, these ammonia particles are going to hit each other more, which means we're going to get more successful chemical reactions in the products compared to the reactants, which means that we would expect the rate of our reverse reaction to increase, and therefore, if the rate of our reverse reaction increases, it is now greater than the rate of our forward reaction. Because of this, NH3 is going to be broken down into its reactants at a faster rate than it is produced, so we would expect the equilibrium to shift toward the reactant side. Because we're consuming more NH3 than we are producing it, we would expect the product concentration to decrease over time as NH3 is consumed at a faster rate, and conversely, we would expect the concentration of our reactants to increase. Now, we can represent this on the graph that we see here. This is a concentration time graph in which the concentration of all of our reactants and products is listed on the y-axis in moles per liter, with time as the variable on our x-axis. We can see that this graph is subdivided into three distinct sections, the first of which here is what we call the I section, because this represents the initial conditions of our reaction before the equilibrium shift occurs. Right after the I section, right here, this corresponds to the stimulus, which is the change that we made to the equilibrium system. And again, we see that this is an instantaneous spike in the concentration of NH3 because that's what we added in order to cause the equilibrium shift to occur. This is what we call the C section, which is why we call it the change section, because this is where the equilibrium shift occurs, and it occurs exactly as we predict. Because we increase the concentration of NH3, that means that it is going to have more collisions, which means that it is going to break down at a faster rate than it is being produced, which is why we see that there is a concentration decrease with NH3 and a concentration increase with both nitrogen and hydrogen gases. Eventually, this concentration change is going to stop, and our concentrations become constant once more, which is why we call this the E section, because this is the point where our new equilibrium has been achieved. Now, if we look carefully at the magnitude of change for each of the three reactants and products that we're looking at, we don't know what these magnitudes exactly are. We can't put a number to them. So instead, I'm going to designate the smallest one of them as X. So we can say that the concentration of nitrogen gas has changed by a magnitude and direction of positive X. Now, if we look here, we see that the magnitude of change of ammonia and hydrogen gas is much greater than X, and that these ratios actually occur relatively regularly. If we look at the magnitude of change for ammonia, we see that it is about double the magnitude of change of nitrogen gas, but that it's a decrease instead. So we can designate this as being a change of a decrease of 2x. Likewise, with hydrogen, we see that it is significantly greater than the magnitude of change for nitrogen, and if we eyeball it, we see that this magnitude here is approximately triple the value of the magnitude of change of nitrogen, which is why we can represent this change as being a gain of 3x. Now, these numbers here are not accidental, and if we look at the chemical reaction here, we see that these magnitudes of change correspond to the stoichiometric ratios that we see in the coefficients of our reaction. Nitrogen has a coefficient of 1, which is why we designated it as positive 1x. Hydrogen has a coefficient of 3, which is why it is designated with a magnitude of change of positive 3x, and likewise for ammonia, negative 2x. Now, what this allows us to do is, if we know the initial concentrations of all of our reactants and products, and if we can figure out what X is, either by calculation or by actually measuring it, we can figure out what these new equilibrium concentrations are mathematically using a tool that we call a Rice table, such as the one that we see below. Each of the letters in Rice represents a different aspect of the table, so the R is simply a statement of the overall equilibrium reaction at the top, and then each of the ICE represent the 3 different stages of the equilibrium shift: the initial, the change, and when the new equilibrium has been formed. Now, even if we don't know what the initial concentrations are, we can still algebraically figure out what all of them are going to be. So let's just write in a concentration placeholder here. And we know that each of the changes is going to occur based on the stoichiometric ratios, and if we know that a concentration increase of NH3 is going to push the reaction in the direction of the reactants, we know what the direction of each of the changes is going to be. So nitrogen is going to gain concentration by a magnitude of positive X, hydrogen by a magnitude of 3x because of its coefficient, and ammonia's concentration is going to decrease by a magnitude of 2x, which means if we take our initial concentration and add or subtract the concentration added by the change, we can figure out what our new concentrations are when the new equilibrium has been achieved. One important thing to note, a lot of students when dealing with the calculations get hung up on the stoichiometric ratios because of how they handled stoichiometry calculations in Chemistry 11. The important thing to note is that the change category on our Rice table is the only time when the ratios between each of the reactants and products are equal to the stoichiometric coefficients. A lot of people think that they are doing these calculations improperly because their final concentrations don't match the 1:3:2 ratio of the stoichiometry, but remember that our equilibrium concentrations depend on the initial concentrations that are listed, and therefore it's the change category which is the only category when the stoichiometry coefficients match exactly. In the next series of videos, we're going to use our knowledge of the initial change and equilibrium phases of an equilibrium shift in order to mathematically calculate the concentrations of reactants or products in equilibrium systems.